Civil Engineering Academy.
Hey there, engineers. Welcome to Civil Engineering Academy, where we're looking at a problem from structural analysis. More specifically, we're looking at statically determinate structures. And the problem reads like this. Find the magnitude of the reaction at support B. So let's look at this beam and try to decide whether this is statically determinate. So if we look at this, we've got two types of supports here. This is a pin support. This is a roller support. This support can be defined by two reactions. So since that is in the y direction, I'm going to call this A sub y. And we'll have another reaction right here. Sorry, that's not the best drawing in the world, but there's two reactions there. We'll call that one A sub x. And then a roller is modeled with a single reaction. Since it's up, we're going to call this, or excuse me, since it's in the y direction, we're going to call it B sub y. So we've got three reactions on this beam. Now, the problem is asking for just the reaction at support B, so we're just solving for By. But a quick way to look to see if a beam is statically determinate is to look at the number of reactions given the type of supports that the beam is sitting on. Given the number of reactions, and remembering from statics that we have three equations essentially, we can sum the forces in the x direction and set those equal to 0. We can sum the forces in the y direction, set those equal to 0, and we can sum the moments about some point. I'll say MP. We can sum those up and set those equal to 0. And we can generate three equations for a given problem. And so if we generate three equations, we've only got three unknowns. Three equations, three unknowns. We can solve those types of problems. Anything that would exceed, if we had another reaction here, say a B sub x, if this was another pin support, we'd have to determine that this thing is statically indeterminate because we'd have one more unknown than we'd actually have equations. And obviously there's other methods that we'd have to use to solve this. But this problem we can use traditional statics since we're statically determinate. So let's get into it. Now, since we are solving for just the reaction at B, let's take moments about point A that will eliminate it'll kind of take these reactions out of play, and we'll be able to isolate the reaction at B. So if we sum the moments about point A, and one other thing is we're going to stick with the following sign convention. It's like the right-hand rule. Anything in this direction as far as moments is going to be a positive moment. And anything going the opposite direction, again following the right-hand rule, is going to be a negative moment. So as we look at these moments about point A, we've got 400 newtons acting down at a distance of 4 meters away from point A. We've got a distributed load here. Now we're going to model that as a single point load by taking 100 newtons per meter and timesing it by 4 meters, the distance of the distributed load, to come up with a force of 400 newtons acting in the middle of that distributed load. So if we do that, we're coming up with another minus 400 newtons acting at 4 meters plus, this is halfway in, so we're 2 meters there, so that's 6 meters. plus, now this is a positive moment, right? We're going this direction with this reaction. So this one's going to be a positive by times this total distance, which is 8 meters. And all that equals 0. Okay, so continuing on, we get minus 1,600 meters minus 2,400 Newton meters. There's a Newton meter there. Plus by 8 meters equals 0. We combine those, we get 4,000 Newton meters plus by 8 meters equals 0. Excuse me, this is a negative. Let's take everything over on the other side. So we're going to have a by times 8 meters equals 4,000 Newton meters. Divide both sides by 8 meters. And we get by equals 500 newtons. It's because those meters cancel out, which is answer B. Hopefully that helps you out, and we'll see you on the next one. Thanks.